So we're happy that you will now continue with this third lecture.
Okay, thank you. So last time we talked about minimally supersymmetric theory in 2D, and then we used stable homotopy theory to make some non-trivial statements about VOAs and Symétries. So, but this time we are going to return to a more familiar world of QFTs. So, if you didn't understand, if there's something that you didn't understand last time, you have good excuse because it's about stable homotopy theory. This time there should be no excuse. So if there's anything that is unclear, please feel free to ask. So QFTs can come in different ways. So I mentioned before that they can be obtained by topologically twisting of some theories that are supersymmetric, like 2D, 2-2 theories. But however we get it, once we have a 2D QFT, then we know that we can study those using the familiar TS-equal axioms. So we know that the QFT functor should assign S1 vector space. And then we know that it should be an algebra because the pair of pens give you a map from two copies of V to V. Furthermore, this algebra is supposed to be commutative because you have topological invariance like this. So this is commutative algebra. And furthermore, there is going to be an inner product because this particular cobordism will give you a map from two copies of V to the ground field. In this case, let's assume that is the complex numbers. And this is again had to be symmetric, so inner product. And also, you will have a unit given by the cap. That's a map from C to V. And then if you look at the image of 1, then that's mapped to some elements in V. And then it's easy to convince yourself that this is going to be the unit. Then, as you have already seen a couple of times, they have to satisfy some consistency relations. For example, the familiar one coming from having these objects to be decomposed in several different ways. So, for example, this will tell you that if you take the products of two elements and then pair with the third, this has better B, A paired with B times C. So here I'm using dot to denote the product and bracket or parentheses to denote the inner product. So if we require a TS-equal axiom to be strictly true, then it's obvious that this has to be a finite dimensional algebra. Sometimes in the world of physics, it's okay to have infinite dimensional algebra in this case. But let's assume that this is indeed finite dimensional. Then all of these axioms will tell you that this is indeed a commutative Frobenius algebra. It's a familiar statement that 2D QFT is the same as a commutative Frobenius algebra. So let's so today we are going to well, first talk about some concrete examples of 2D QFTs, but we are now going to study them in their own sake because in this context, it's not going to be terribly interesting. So what we will do is that we will use 2D QFTs as stepping stones to get more interesting theories, either 3D QFTs, or even, in a sense, 4D QFTs, and also theories that are not topological in 3 and 4 dimensions. And the 2D TQFT, or the community formulus algebra that we will use for this purpose, is the familiar Berliner algebra that many of you had already known. So to define a Berliner algebra, I will take compact Lie group G, and then an additional piece of data known as level. So in full generality, I will be allowed to take anything in H4 of BG with Z coefficients, or it can be even more general. But for today, we are going to talk about groups that are either simple or U1. So for our purpose today, this is going to be Z. And we actually take K to be non-negative. And then Berliner algebra is going to be something quite simple. So it's going to be a quotient of the representation ring of G. So in the representation ring, there are familiar products given by tensoring two representations and decomposing them. And then to get the Berliner algebra, you want to impose some relations that would actually depend on K. To give an example, let's consider U1 at level K. So in this case, V would be K-dimensional, and there is a nice basis that I will denote by E0 through E K minus 1. And then the algebra structure is given by EI times EJ equals to EI plus J. And the relation is going to be given by I plus K equals to EI. So it's easy to check that indeed this is K-dimensional algebra, and it's a very simple algebra. And furthermore, the inner products of E and EJ equal to delta IJ. And this will make this Frobenius algebra. So what is this algebra? Have we seen this somewhere in geometry, since we are emphasizing connection with geometry? This actually turned out to be the quantum cohomology of CP K minus 1. So CP K minus 1, the quantum cohomology of this would have the same dimension as the usual cohomology. So we know that this is indeed K-dimensional, and then there is going to be a generator X in degree 2, and that also generates this. And to get isomorphism between this quantum cohomology to the Berliner algebra, you just have to send X to the I into EI. Something is a little bit funny, because we know that here the relation is quite different from this relation. So here, if we take, for example, X to the K's power or any higher power, it will be 0. But this is a classical relation. In quantum cohomology, this is replaced with either Q or in our normalization, just 1. So this is not just a coincidence. So if you consider a 2D 2,2 sigma model onto CP K minus 1, then you can actually perform topological twist, and this is what you will get. So you see that you can get this 2D QFT in different ways, either just by starting with abstractly this commonly formless algebra, or you can start with some physical theory and then perform this topological twist. So if we are just in one dimension, then we only see cohomology. We will not be able to see an interesting product structure. So in 2D, we have an interesting ring with some quantum corrections. Also, if you look at boundary conditions, there's going to be some category associated with basically related to Foucault category of CPK-1. So in a sense, by going from 1D quantum mechanics to 2D theory, you are actually categorifying, getting some thing that is more interesting. But of course, I will not go into Foucault category. So instead, I will switch to the next example. But before this, is there any question about this basic example? So the next example is SU2 at level K. So now the dimension of V is going to be K plus 1. And then I will take there's nice basis. So E0 through EK. And then if I take EI times EJ, I'm not going to have a single, in general, a single EK somewhere. So I will have fusion rule given by F, I, J, let me use L, summing over potentially a bunch of ELs. But the inner products is still such that this is delta ij. So to describe for you what this commutative formless algebra is, I just need to tell you what is F. So I will write it with all lower indices. So this F can only be either 1 or 0. And it can only be 1 if the sum of I plus J plus L is even. And furthermore, I, J, and L, so this triple, live inside a tetrahedron. So what do I mean by this? So if we have, we have 3 indices for the fusion coefficients. And we can imagine a cube of size k by k by k. We take these 3 special vertices along with the origin, and we have a tetrahedron like this. So I'm not drawing it terribly well, but you can, I guess you can clearly see there's a tetrahedron. So if the sum of all the labels is even, and then if the point that this ijk represents is inside the tetrahedron, then this can be 1, and then it's 0 otherwise. So there are 4 faces of the tetrahedron, and then there are 3 faces that correspond to familiar relations. For example, it's telling us that I is not supposed to be too large compared to the size of J and K. So if you tensor 2 small representations, there's no way to get a really big representation. Similarly, if you tensor a big representation and a smaller representation, in the decomposition, you are not going to have a very small representation. So that's the meaning of the 3 faces that pass through the origin. But then there is a 4th one, and that's some affine relation going on. So to give an example, usually if you multiply 2 times 2, you get 4, but in the representation ring of SU2, you are supposed to decompose this into 1 plus 3. In this basis, what you would write is that E1 times E1, that's E0 plus E2. So this would in general be true, but if actually K equal to 1, so what happened is that actually 3 equal to 0. So then you have actually just 2 times 2 equals to 1. This is nice and simple for Venus algebra. So any question about this? So because this is not only just an algebra, it's something that can give you a 2D QFT, then you should be able to talk about partition function of the 2D QFT on any Riemann surface. So let's assume that sigma is a genus G Riemann surface. Then, in a famous paper by Valinda, he pointed out that there's a nice way to make the fusion rule diagonal using basically the S matrix. And if you diagonalize the fusion rule, then you have a very simple expression for this partition function that basically looks like this. So you can compute a partition function on genus G Riemann surface either using this formula, if you are able to find those. So I will also write this as S0I, but you can, if you can forget about S transformation. Instead, you can just try to diagonalize the fusion rule. So if you diagonalize it, then you will find these numbers and you compute the partition function. Alternatively, you can just cut a Riemann surface into pieces. So what happened if you let's continue here. Again, consider the case of SU2, and then consider partition function on genus 2 Riemann surface. So in this case, you have nice and simple formula 1/6 k cubed. It's always going to be function of k plus k squared plus 11/6 k plus 1. So that's the partition function of that 2D QFT on a genus 2 Riemann surface. So believe it or not, this is actually going to be an integer. And since it's an integer, you can ask, is it counting something? So there's a quick way to find the answer to this problem by indeed decomposing this genus 2 Riemann surface into 2 pair of pens. So then you know that this should be the summation of Fijk squared. And Fijk is either 1 or 0. So you are summing over the ones. So that's the number of points or even points inside the tetrahedron. So, or you can find something else that is a little bit more fancy as the answer to this question. So another possible answer is that this is dimension of the space of homomorphic sections of the line bundle O case power of the topological line bundle over CP3. So why is that the case? So if you still remember how to count homomorphic sections, you realize that exactly correspond to a number of points inside the tetrahedron. Why is that the case? So here we are supposed to look for polynomials in 4 variables of degree k. And then the generators are monomials. So like x to the k, y to the k, z to the k, w to the k, and then you can fill in this tetrahedron. Right, so x k minus 1 times y and so on and so forth. So that's exactly the number of points. So what is is this just a coincidence? Am I just trying to find some manifolds that happen to satisfy this property? It's actually not an accident. So here, the role played by this CP3 is very different from that CPK minus 1. So there, what is the manifold? It will depend on K. But here it's independent of K, but instead the line bundle over it depends on K. And this CP3 is actually the moduli space of flat SU2 connection on sigma. Alternatively, you can view this as a moduli space of stable SL2C bond. So it is generally true that this particular function is counting number of homomorphic sections like this. So what do I mean? So if I use M to denote the moduli space of flat G connection over Riemann surface sigma, or equivalently, the moduli space of stable GC bundles, then over that there is a nice line bundle, sometimes referred to as determinant line bundle. And then I can raise that to the case power. And then the partition function of that 2D TQFT is always giving dimension of this. This also depends on G and K. And then I'm talking about partition function of sigma. So this seems to be a nice facts that relate something in the algebra world to something in the geometry world. So, but as I mentioned before, this will just be a stepping stone for us. So we are going to consider moving away from this formula in 2 different ways. So one way is by trying to replace G, which is a compact Lie group, by the complexified version. So this is something that would not be allowed in the original setup. But here, because we have geometry, then this becomes meaningful. We can either consider the moduli space of flat GC connection on sigma, or this is also famously known to be isomorphic to the moduli space of Higgs bundles, GC Higgs bundle, Riemann surface sigma. And then over there is a similar line bundle. We can take that to the case power, and then we can ask whether it would be interesting to look at the space of homomorphic sections of that. So this is a very interesting moduli space that we will encounter again tomorrow. So one thing that I want to mention now is that there is, well, to help you visualize what this space looks like. So it emits a vibration known as the pitching vibration. So the base is affine, and then the fibers are generically special Lagrangian tori. So this space famously emits a hypercalorimetric, and then it makes sense to talk about special Lagrangian subspaces, and the fiber are exactly generically special Lagrangian tori. And then there can be some singularities. For example, I can easily have something that looks like this. Another interesting feature of this space is that there is a U1 action, sometimes referred to as the Hitching action, that acts as isometry. And over the base is just some rotation around the origin. But over the entire space is some interesting non-trivial action. And all the fixed points are going to be inside the central fiber. So as a consequence, although this is a non-compact space and you expect that this is infinite dimensional, it can be decomposed into finite dimensional subspaces that has a fixed weight under the U1. And then here, what we can do is that instead of talking about the dimension, we just introduce a parameter. And then we instead look at the t dimension, simply defined as dimension of the weight n piece times t to the n summation over n. So this seems to be some reasonable thing to do. And then the question is that, well, before, what's special about this formula is that it's a partition function of a 2D T graph T. What happens now? So here, the observation or the theorem is that this is again partition function of 2D T graph T. But now it's a one parameter family of 2D T graph T dependent on the value of T. So this would depend on T. And then if you evaluate that on sigma, that's again giving you this graded dimension, this T dimension. And to tell you what this 2D T graph T is, I just need to tell you what is the commutative Frobenius algebra. I'm supposed to just take this and add T somewhere. So what I'm going to do is that for the fusion coefficient, I'm going to have T to some power. And this is when I plus J plus L is even, but I, J, K is not inside the tetrahedron. And in fact, the delta here is defined to be the distance through the tetrahedron. So that's my F. And then the inner product now is also deformed. It's still proportional to delta Ij, but then there is a coefficient that has T dependence. It's either 1 minus T squared or 1 minus T. So it's 1 minus T squared if I is either 0 or K. And it's 1 minus T if S not 0 or K. Then you can verify that this is still commutative Frobenius algebra. And this kind of construction exists not only for SU2, but it's true in general. So here, this expression is supposed to be for general, let's say simply connected G. For the algebra, it's now deformed. So before we have 2 times 2 equals 1 plus 3. So now we'll have something that is T dependent. So let me put it over here. So if I still want to compute 2 times 2, then I will have 1 over 1 minus t squared, 1 plus 1 minus t 3, plus let's assume that k equals to 6. So there are 2 more terms to worry about. And I have 1 over 1 minus t times 5 plus 1 minus t squared times 7. So that's now a different algebra. Notice that if I expand this in series in t, I'm having positive coefficients. That's actually a generic feature of this partition function. So any question about this deformed 2D T cavity? Yes.
So if you set t to 0 in the algebra, you get back an equal to algebra, I guess?
Yeah, that's exactly true. So if I
geometric side though, what does it mean?
Yeah, geometric side. Yeah, geometric side is also mean that inside this U1 action, so this space sit inside the bigger space, and then that's the particular components of the fixed points.
Yeah, but why does it agree with like what the other GOT would assign?
Right. So the statement is that here, if I'm just looking at n equals 0 piece, there is a simple geometric argument that that's exactly homomorphization of this line bundle over this guy.
What's the simple geometric argument?
So so let's imagine that this is a T star of this.
Okay.
Then this has a simple interpretation in terms of symmetry powers of the cotangent bundle to M.
Oh, and like the C star is the cotangent dilation.
Yeah, exactly. So in that case, it's obvious, but it's not a cotangent bundle as a space. It's actually a cotangent stack. So that's good enough.
One other question. Where did the Q, like the Novikov variable, come from in example 1?
Q?
Yeah. Like
You mean that Q?
Yeah, where did that? Where did it Q? Like in the beginning, you just say given V is K, but like at some point you have to extend your base field, right?
Oh, so here I will just set Q to 1, but you can keep it. If you want to keep it, then indeed you either treat this as a number or as a formal parameter. From the physical point of view, maybe you should better treat this as actually a number. Then it's actually not too different, right? It's just a number. A number is 1 is also a number, so
Yeah,
yeah.
but not 0. Yeah.
Right. Mm-hmm.
I mean, I would want to ask what this means categorically, but this will come at some point.
Right. So,
Okay.
well, that's actually the question that I'm going to ask you.
Okay.
So, any other question that does not involve categories?
A silly question. So is there even just a hand waving reason as to why we extend, for example, this fusion rule so that the 5 and the 7 appear? Because 2 times 2 is 1 plus 3.
Sorry. I'm missing
There's t's on top.
yeah, there's a t and t squared, so that in the limit that t goes to 0, they indeed become the old fusion rule. Yeah. So there is a geometric argument for this. So if you look at the model space of bundles on the 3-hole sphere, then if the triangular inequality is not satisfied, this space is empty. But then for model space of Higgs bundles, it's actually non-empty, because the Higgs field can do something so that there is still some solution. And that's basically the reason why this appear, but with some power of t. So any other questions? So so this is one way that we are going to move away from Verlander algebra. The other way is well, obviously in a categorical direction. So So let's denote the linear algebra again by V. So it depends on G and K. Then this can be categorified in the sense that it becomes the quotient degree of some category, and that's a familiar category. Let's know it by rep GK. That's a model tensor category. So physically, this is saying that this 2D QFT is a dimensional reduction or reduction of S1 of a 3D QFT. And that 3D QFT is a famous one. That's a Chern-Simons theory. And indeed, to define Chern-Simons theory, exactly you want to have a gauge group and then a level. But how about this deformation? So here there is a one parameter family of deformation parameterized by T. We know that we're not supposed to deform model tensor categories. So when T, so if we set T equals to 0, we get this. For T equals to 0.0001, there should not be a model tensor category. So this, but physically, we still expect that there is some category where we expect that this is the case. This is because this can be also constructed physically from a 3D theory, but it's not topological. It's a 3D n equals to 2 Chern-Simons matter theory. So a 3D n equal to 2 theory, you cannot twist it to be topological. But then if you reduce it, it becomes 2D 2,2. And that's actually large enough supersymmetry to be twisted. So it can be 2D 2,2 / topological. So this theory is not topological, but in 2D it becomes topological. So what would that tell us about the category? Because it's not topological, you actually expect that the category should consist, there should be infinitely many simple objects. So first of all, it depends on G and K. It should not depend on T. So there should be infinitely many simple objects.
What is C?
Oh, so it's some category. Physically, it's the category of line operators of the 3D n equals 2 theory. So we know that this should exist, but so far there is not enough effort to fully characterize this category. But we do know that it should better have many simple objects. There should also be fusion, and then there should also be braiding. And then we also know that when we reduce, we can get this. So here the picture is that here there's only finitely many bases. So but for a given one like E, J, over here there should be an entire tower. So there should be a tower of objects that collapse in such a way that the fusion upstairs, oh, I have already erased the deformed version of this, in such a way that the fusion upstairs is compatible with a deformed fusion downstairs. And then there should be another way to reduce this to a model tensor category. So that's all the information that I have about this category at this moment. So, and the question for you is to it should not be a model tensor category. Well, so you have infinitely many. It could be as something as simple as semi-simplification, or it could be something more complicated. So physically, it corresponds to So what's happening here? So this is a category of line operators. So these are Wilson lines, though by some representations. Here, there are also Wilson lines, but they can be addressed in some way. And also, this representation can go outside the usual normal range of integral representations. So, so you seem that maybe some simplification is relevant, or there could be something else that is going on. So
Sorry, the fact that it has this T, does it mean in some sense you expect that there is some chronological degree which the T encodes, the T coefficients, or I mean, is that the interpretation of your mind?
Yes, so the exact statement is that this theory actually also have a symmetry. So there is a U1 action, and that should also mean something here. So, but because this is a global symmetry, I would not say that this is a cohomological grading. So it could just be an additional grading.
It's the U1, why do you want n equals to supersymmetry, or is it separate?
So it's a separate, so it acts on the matter part. Yeah. So one can ask the very general question that if I have a 3D equal 2 theory, what should I do? That seems to be a little bit too hard. So, but this is like the simplest possible equal 2 theory where you can ask this question basically and still have a non-trivial answer.
Guess what the matter is?
Yeah. So here matter. So you need to specify the representation. So this is like a joint. So recall that it's somehow related to a complex transamination theory. And then if you somehow view complex transamination theory as transamination matter theory, indeed, you want the adjoint representation.
Pretty close to n equals 4 pure H theory.
It's quite close, but there's a transaminance term that spoil this. So this is another way of saying that this is kind of a simple theory. Right. So for really 3D equals 4 theory, you kind of know what the category of line operator should be.
Yeah.
So, but with this transaminance term, it become non-trivial.
You expect it to be category of line operators in the holomorphic split that should feature here?
So we are asking about the category of line operator with a holomorphic twist. So otherwise, there should be some non-trivial OPEs going on. So in the full theory, then you have some non-trivial OPEs, similar to in a conformal theory. So here, we can first perform this homomorphic twist, and then ask for what this category should be. That should be a simpler first step. Then maybe one can also figure out this a more interesting structure with OPEs. So any other question?
Oh, could you see what the T deformation is in the U1 example?
Oh, in the U1 example, it only modify this into 1 minus T delta ij. So it's something simple and boring.
And the tensor product stays the same.
Yeah, that's right. Other questions?
Can you say what it is in terms of quantum homology? Is it the covariant quantum homology?
So that was floor homology?
Is it? I was asking if you can say what the definition is in terms of quantum homology.
Quantum cohomology.
Because
Yeah. So it's quantum either cohomology or K theory of CP K minus 1 times C, and then you have the U1 action on this factor. So equivariant with respect to this U1. So in this case, it's boring because, well, it's just a standalone factor. And that's also why it's just factorized. In the non-abelian case, this is replaced with something more fancy. some vortex model space that I will not bother you with. Because it's related actually to 3D theory. And 3D theory, you always have K theory for 3D theory. So in the case of cohomology, so when we can study this, he first used cohomology. But there's actually already some subtlety, like why fusion rules are or integers. That's not explained by identifying that with quantum cohomology. But if you go to quantum K theory, that become like natural. Yeah, so the modern point of view is that you should always use quantum K theory in this case.
May I also ask a question, Luke?
Yes.
So the first case we talked about comes just from the Westermino-Witt theory.
Yeah.
So that's just coming from the affine VOA at integer level. And so could it be that your bigger category is and that's the simple affine VOA. So do you expect your bigger category to be related to the universal VOA? Just you don't take the simple quotient, then it has much more modules. Is that the way to think about it?
I'm not quite sure. So at some point, we were thinking about WW model for the complex group.
For the complex group, yeah, which I think would just amount not to taking the simple quotient.
But then there is some subtleties. So we're not quite sure whether WW model with a complex group is a right model for it.
Yeah.
So somehow.
Yeah.
So the U1 action is not very compatible with the complex structure for GC.
Which U1 action?
Right. So this U1 action that we use, so it's homomorphic in a different complex structure. It's in the complex structure that comes from the Riemann surface, but it will rotate the complex structure associated with GC. So therefore, somehow GC WW model might not be the right approach, but it still could be. So,
or is physics suggesting anything what it could be?
I guess physics just suggests this should be a category of line operators in the 3D theory.
Yes.
So there might be other suggestions that I'm not aware of.
There are these strategies to guess these big categories. Sometimes, like using a category of organization. Like what just there's probably best for this.
Right. So I still have it here. So I was talking about transamination theory, and to just continue exploring this direction, let me mention that well, it seems that today we're having a resurgence of path integrals. So maybe let me write down the path integral for transamination theory, which is actually something relatively simple. So the variable here, A, that's a connection of G bundle over, let's say, a 3-manifold M3. And then this is the transaminance form. And locally, it looks like ADA plus 2/3 A wedge A. And then here, K has to be integer for this to be properly defined. And then if you perform this path integral, you are supposed to get invariance of 3 manifolds. So that's the WRT invariant, WRT for Witten, Reshetikin, and Tulev. So it's the invariance of M3, and of course also depends on G and K. So there is similar closely related invariance, but not of manifold instead of by considering observables. So one can consider not. I'm again having trouble drawing a reasonable knot, maybe something like this, colored by some representation. And then let's assume that this is in S3. So this is observable. So it's a path integral with an insertion. So you have the same path integral, but then with trace of the connection. So you take the holonomy along this knot, and then take the trace in representation R. So maybe I'm not writing it in the proper way, but you know what this is. And then an interesting fact is that this can be written in terms of the variable q, that is 2 pi over k, potentially with some shifts involving the two constant number, but I'm ignoring that. So in the simple case where we have the SU2 and the trefoil knot, colored by the two-dimensional representation, then this is q plus q cubed minus q to the fourth power. I hope I got that part correct. So this is something that is rather special as either a partition function or correlation function, because all the coefficients are integral. And this is explained by Polanov, who tell us that one can categorify this knot polynomial by problem of homology. So there's going to be some abelian groups that you can associate with this knot. And then if you take some certain order characteristic, you're getting back this knot polynomial. And one question that has been bothering many people is how to categorify the WRT invariance. So to see that this is actually a non-trivial problem, you just need to look at some very simple examples. So if you take your three manifolds to be the length space L5, 1, so this is a particular quotient of S3 by Z5. Then what is the WRT invariance? Can we write it again as a polynomial in Q? So if we first factor out I times square root of k, which is already not so nice looking, we are still left with something that involves, first of all, 1 over square root of 5, that's not an integer, times this, and then plus something that is again not quite integral, and involve k in a different way. So for this, you will not be able to write it in terms of q easily. And then some irrational coefficients appear again. You get the idea. So if we are looking for polynomials in Q, there are some with fractional powers, but then there are some numbers that are not integral. So it's hard to imagine categorifying this in the similar way. So then should one just give up on the effort to categorify the WRT invariance? Actually, one observation is that the WRT invariance is very hard to categorify because it's a wrong object to be categorified. So the solution to this is that we decompose the WRT to some more basic building blocks that I will denote by Z hat, labeled by A. So this is something that perhaps you have already seen before. So the decomposition is such that these coefficients are going to be very simple and very universal, but it will still depend on K and also on M3, but in a very simple way. So all the interesting quantum topology is carried by Z hat. And for Z hat, A, so this is going to be an integral series in Q up to a shift. And here, A is valued in torsion part of H1 of the three manifold. So in the case of length space L5, 1, what happens is that, well, now if you look at H1 is Z5. Portion part of that is again Z5. So there are supposed to be 5 Z hats, but there's a symmetry. So we only have Z0 hat, Z plus minus 1 hat, or just denoted by Z1 hat and Z plus minus 2 hat. And they are respectively -1 due to 1/2 and 0. So in this case, they are actually very simple, but that's a special case. In general, it's actually infinite series in Q. And then all of these non-trivial coefficients, they just come from the C's, and they are universal. So then you see that the coefficients here are all integral. And the statement is that they can be categorified. So the proposal is that, first of all, Z hat in this way, satisfying this property exists. And then it can be categorified by some abelian groups, some new type of homology associated with the three manifolds that is labeled by A and then 2 integers, such that if you take Euler characteristic with respect to one of the variables, then Q to the ith power, and then summing over Nj, then you will recover the Z hat. So the question that we are going to answer either today or tomorrow is why do we expect that they exist? I will provide some physical way of justifying this proposal. And the question that I will not be able to answer, but instead I will just ask this, is that why they are actually characters of VOAs or log VOAs.
What do you mean? What are they?
Oh, Z hat. Yeah, Z hat are infinite Q series, and then there is the observation that for whatever three manifolds, if you work hard enough, you can always find some log VOA whose character is exactly Z hat. So from physics, it's not so hard to predict that there are actually Z hat, but actually slightly more non-trivial to find the argument why this log VOA has to exist. That's a question that we will explore either later today or tomorrow. So for now, I'm going to ask actually more questions by moving one dimension up. We'll look at 4D QFTs, unless there are questions about 3D or 2D theories. So all clear? Right. So we have already encountered several 4D QFTs in this program. So some of them are pretty good. For example, they have maybe potentially can detect exotic smooth structures. Some of them might only know about signature or the characteristic of the four manifolds. So it seems that the most, from the point of view of 4D topology, the most useful invariants are obtained from quantum field theory. So these are invariants such as Donaldson invariants and several Witten invariants. But in a sense, they are still not very strong. So maybe you you don't know the complete detail of them, but maybe you have heard that the invention leads to a lot of action in the field of 4D topology, and there has been like various theorems proved using these invariants. But you should not have the impression that they are really strong invariants, because they're actually zero in many cases, or maybe I should say in most cases. One way to get zero is by looking at several Witten invariants associated with kinetic sums. And this is going to be zero if you have M4 and M4 prime. You have several Witten invariants defined for them individually. And then you take kinetic sum, then it's going to be zero. And that's one way of getting zero. There are actually a lot of ways of getting zero. So for example, if the Betti number is not correct, then it's zero. And then there are many ways of getting zero. So can we do something that is slightly better than those invariants? So first one should ask, what's actually wrong with those invariants? The answer seems to be that they come from 4D theories. So what do I mean by this? What I mean is that they are topological twists of actually 4D n equals to 2 QFTs. So we will say more about 4D n equals to QFTs. But here, I just want to mention that because of the 4D origin of those invariants, they are very easily zero. If this is a problem, then the solution is simple. We just consider quantum field theory in even higher dimension. So a simple solution is that we consider higher dimensional QFTs. So if 4 dimensions is not high enough, then we consider 5-dimensional or 6-dimensional theories. So why not 7-dimensional or 8-dimensional theories? We know that if we just want quantum field theories, free theory exists in very high space-time dimensions. But probably we should not use free theories to, if our goal is to get interesting invariants of manifolds or interesting 4D QFTs. So if we want interesting theories, then there is a famous statement by Nam that 6 dimension is the highest possible to have interacting and superconformal quantum field theories. So SCFT stands for superconformal quantum field theories. And in 6 dimensions, there are 2 types of theories. They are often referred to as 6C 2,0 theory and 6C 1,0 theory. So why I'm again using this notation? Well, 6D is similar to 2D in the sense that you can talk about spinors of 2 different chirality. So they are, in a sense, also left-moving and right-moving spinors. So the supercharges are going to be in a particular chirality. So for this type of theory, there is a classification. So they are classified by ADE Dinkin diagrams. So they have ADE classification. So basically what this means is that this can actually have different factors. You can have a bunch of abelian factors. And then you can have different other sectors labeled by ADE Lincoln diagrams or ADE simple Lie algebras. For 1,0 theory, there is no complete classification yet, but we know many theories are labeled by singular, elliptic, Calabi-Yau threefolds. So to give some very simple example, you can consider T2 times C2 mod gamma. That's elliptic because, well, there's a T2 factor. It's singular, clearly singular here. And if you want to classify the singularity, that's indeed something classified by ADE. So this is a way of embedding 2,0 theory inside the world of 1,0 theory. So they are special kind of 1,0 theories. But then you see that it can be more general. So I imagine this to just give you a feel of this world. So we are going to later, we are going to use primarily 62,0 theories. And then you just need to keep in mind that they are labeled by ADE Lincoln diagrams. So what can we do with those theories? So if our goal is to understand invariance of 3 manifolds or 4 manifolds, either that or try to produce something like a VOA or some algebraic structure that we want to understand. Six dimension is a little bit too high. So then, but we can consider the 60 theory on some geometries. So what we would not want is just some 6 manifolds. That would be too generic. Also, it's going to be hard to preserve supersymmetry in any way on a generic 6 manifold. So we're going to maybe consider some possible geometries and then see what we can get from the 60 theory. So can anyone suggest some geometry that on which we would like to study the 60 theory? So let me offer one that is also not very good. That's S1 times M5 or R times M5 with a generic 5-dimensional manifold. So what happens here is that I can actually preserve supersymmetry here. So then if I reduce on the 5 manifolds, I'm going to get theories that are labeled by the 5 manifold. Let me denote it by T of M5. And those are 1D theories because I'm reducing 60 theory on a 5D theory. And those are generically 1D, n equals 1, quantum field theory or quantum mechanics. So in principle, we can get some invariance of 5 manifold in that way. If you, for example, look at the weight index. But no idea what that should be and whether there can be a stellar application to the study of 5D topology. So let's pass on this. So any other geometry that we can study with those theories?
We could take a surface in the 4 manifold.
Yes, that's a very nice choice. Sigma times M4. So here, I haven't specified which theory that we can use. If we want to use the 61,0 theory, we'll be forced to have T2. Otherwise, again, we cannot preserve supersymmetry. So T2 times M4. And then in this case, if we reduce a 61,0 theory on M4, we're going to have a theory that is exactly 2D 01 theory on T2. For this purpose, I can just take T2 to be R2. So that would be the same. So then what can we do? Well, we can look at the TMF invariant, topological model forms. So we have pi star TMF valued invariants of 4 manifolds. And then you can ask whether those are interesting invariants or not. So I will probably not be able to say too much about it, but I would remark that actually for those invariants, let me just use D for this invariant, it's no longer true that you can easily have this being 0. In general, it's non-zero. So this is already showing some promising sign that is better behaved compared to several written invariants. So this is for 1, 0 theory. And then we can also consider 2, 0 theory. Then what happens is that here in 2D, we're also going to have 0, 2 theory, with again more supersymmetry. And then, as I mentioned before, the Q cohomology of this is going to be a VOA. And this is something that is denoted as VOA of M4. So vertex over the algebras labeled by 4 manifolds. So they are also quite interesting objects. So the first sign of the existence of those date back to the work of Nakajima on instant moduli space, and then later it has developed more, and now it's in a more unified framework. So any other geometries that one should consider?
So, well, so the 2, 0 supersymmetry case, you also needed to restrict the surface to be a torus.
Actually, in that case, it can be more general. Yeah, so there should be a well-defined correlation function on sigma that only depends on complex structure of it. More questions? So
the time is short.
yeah. So let me just maybe mention one thing, and then we end today's lecture. So another geometry to consider is R times sigma times M3. That seems to be a boring variation of this. But this is a geometry that we can reproduce a lot of stuff that we had. So what can we do? So here, if we take sigma to be a disk, what happens is that we are going to have some 1D quantum mechanics living in this R direction labeled by 3 manifolds. And also, as a disk, I should have some boundary condition. Why not denote it by A? And the statement is that this quantum mechanics, the Hilbert space of that is exactly this IJ labeled by A, the categorified Z hat. If I take M3 to be something specific and let R, let sigma to be something that is general, so this would be length space, LK, 1. And then I again get some quantum mechanics. I can take the Witten index, or equivalently, I just take this to be S1. And then I get a 2D TQFT on sigma. And the statement is that this is exactly this deformed within the algebra that we have. So let me end here, and tomorrow we'll explore a bit more possible geometries and connection with VOAs. So there's an interesting difference between these two. So if you have S1, then there's a way of using that S1 to turn on an auto-automorphism of G. And then you can get more general G. Yeah, and then the question is that why, if we somehow decompactify and then like categorify, somehow simply lace is special? That's a question that I don't know how to answer.
You have these conjectures that there are a lot of VOAs associated with 3 manifolds.
So that's the observation that indeed the key head are characters of log VOAs.
Yeah, so do you have an explanation from this kind of physical perspective?
So that's the question. So I do not. So and I hope someone would be able to. Yeah, I can say something. So here, if you replace this with S1, then you have a solid torus. And then if you somehow can open, like replace the origin, replace this by S1 times S1 times interval. Then you can reduce on this interval and then claim that you actually have a 2D theory. So for some class of 3D theory, you might be able to do this, but it's not clear why T of M3 is always in this class. So the short answer is that I don't know. So this is my best attempt.
Do we have more questions? We can continue with many questions in half an hour.
Yeah.
Okay. So let's thank Du.